Climate change is driving an increase in frequency and intensity of wildfires all around the world. The fires in Australia during 2019 and 2020 burnt more area than in any fire season in living memory. Since then, fires have continued to rage around the world, in the United States and most recently in Europe, in response to extreme temperatures. Anecdotally, we're seeing more fire-generated thunderstorms, pyrocumulonimbus, with powerful convective updrafts that increase the intensity of the fires and carry burning firebrands for many kilometers. They may also have important climatic effects, since collectively they add huge amounts of aerosol to the upper atmosphere. We need to know more about how and why cumulonimbus form, and their effect on the climate. Machine learning offers the possibility of detecting all examples of these pyrocumulonimbus using satellite data, and unravelling the causes and effects.
It's an honor for us to present to you our project, which we've been doing for the past 8 weeks, where we try to address the question, what if we could understand and respond much more effectively to wildfires than we can now? So on our team, we have me, so I'm Ashwin Browder. I'm a researcher in remote sensing of planetary atmospheres. We also have Ken Zatazi, who's a PhD student in artificial intelligence applied to environmental risk. We have Emiliano Diaz, who's a researcher in causal inference methods in machine learning. And finally, we have Daniel Oko, who's a researcher in space weather. And we're also very indebted to our faculty and our research advisors for facilitating this project and guiding us all the way. So, of course, it goes without saying that wildfires are extremely destructive. They destroy communities, they destroy ecosystems, they lead to property damage, and more importantly, they cost lives. And so what we have here is a picture of a particularly bad wildfire in Northern California that started around 2 weeks ago, and it's already burnt an area the size of Birmingham, and it's been very, very difficult to contain. And part of the reason why it's been so difficult to contain is because it's been producing these storm clouds that exacerbated the fire even further. So how do these large and intense wildfires cause these kinds of storm clouds in the first place? So the principle is that if a fire is large and intense enough, you'll create so much smoke, which will ascend so high into the atmosphere that the smoke will condense and form clouds. And under certain meteorological conditions, these clouds will form thunderstorm clouds. So these thunderstorm clouds are known as pyrocumulonimbus, or pyro-CB for short. And these pyro-CBs are extremely dangerous for two main reasons. First of all, they cause lightning, which can ignite further wildfires. And secondly, this fire causes unpredictable weather patterns. So it causes turbulent winds, which can fan the flames of the fire even further. And it can also cause the fire to change direction very suddenly and in unpredictable ways. And this poses an enormous challenge for disaster response teams. So only a very small minority of wildfires actually result in pyros, because you need a particularly large and extreme wildfire to do this. But what we're seeing is with climate change that we're predicting a 50% increase in the number of wildfires up to 2100 from here. And what we're seeing is wildfires are also set to become more intense. So the number of intense wildfires that are actually going to lead to these pyro-CB events is going to go up in even more than this. So it's becoming much more urgent and imperative to be able to better understand pyro-CBs. So essentially what we need is a good strategic containment strategy. So what we need to be able to do is identify the wildfires where pyro-CBs are likely to take place, and try to contain those fires as much as possible so that they don't produce a pyro-CB. But we also have to plan and anticipate for the fact that perhaps the containment will fail. So, so we have to plan for evacuating many more people, and if we can do this as early as possible, we can have a much better strategy. And so if in case the pyro-CB causes the wildfire to move in unpredictable ways. But of course, to be able to do this, we need to actually be able to identify which of these wildfires are most likely to produce pyro-CBs in the first place in order to be able to allocate finite resources towards those particular fires. So essentially what we need to be able to have is a machine learning model that can first help us better understand the interplay between the properties of the fire and the meteorological variables that are most likely to cause a pyro-CB, and hence allow us to better predict when a pyro-CB is likely to occur, simply by looking at a geostationary satellite image of a wildfire earlier in the day. So the question we have is, are we able to produce some sort of prediction model that can forecast a pyro-CB given a wildfire earlier in the day? And that's where I hand over to Emiliano, who's going to talk more about the obstacles that we face in doing so. Thank you.
Thanks, Ashwin. So why now? Why hasn't this been tackled by AI before? So the information that we will use at the spatial and temporal resolution that we needed has been around since 2018. And why hasn't it been this tackled before? So it's three interrelated problems. There's we don't know where to look. So that's related to labels. There's a large amount of information that's related to the temporal resolution, which we need the information. And there's also the amount of wildfires that are out there. And there's also the way that the information is organized. So break down a little bit these challenges. So here on the left, we have an image from the Himawari geostationary satellite, which orbits at the same rate that the Earth spins. So it's always looking at one place. And we see that it covers East Asia and Australasia. And on the right, we have the Australian subcontinent, and we have mapped on there the frequency of wildfires during 2019, with blue being a little bit less frequent, and then up until the cyan, which is more frequent wildfires. And so what we see is that there's a very, very large amount of wildfires, and we need some prior detective work in the form of labels to be able to narrow down which wildfires are potentially produced pyro-CB, and then go look at those images and see if we can spot conditions that led to the pyro-CB. And regarding the amount of information that there's out there, as we mentioned, we need high temporal resolution. These satellites provide that. They provide 10-minute frequency of observations. On the left, as before, the Himawari. On the right, we have the GOES satellite, which looks at over the Americas. However, if we have the detective work, we would be able to just download the little square, the little red square, which represents our label. However, because of the way that the information is organized, we actually need to download the whole of the image disk and then crop out the area that we're interested in. So that was one of the big challenges. So basically a download bottleneck where we had to develop the tools to be able to download these large amounts of information. So Ashwin talked a little bit about the need for a 6-hour ahead prediction model to aid containment and evacuation efforts. And I talked about the challenges, and the challenges refer more to the database, to be able to develop the database so that we can go on to the forecasting. So we identified these three components that we need: the database, which includes data, images, weather, labels, and download tools, the forecasting model, and also a discovery framework within which we can try and interpret results from the forecasting model and sort of feedback on the modeling efforts, but with a more robust sort of causal understanding of pyro-CBs. So this is why we're very proud to present to you Pyrocast. It integrates these three components. It's an end-to-end machine learning pipeline that aids in analysis and forecasting of pyro-CBs. And I'm going to pass on to Kenza, who's going to talk about the first two components, the database and the forecasting model. Take it away, Kenza.
Thank you, Emiliano. So to create a database, we start by curating historical pyro-CB dates and locations from blogs and sparse online databases. And then we match these with global wildfire records from the GlobFire database. The next step is to find the satellite image data. Most Pyro-CB events are located in North America and Australia, and we also need to get a good temporal resolution to study the evolution of the wildfires, as Emiliano mentioned before. We therefore choose Himawari 8 and the GOES 16 and 17 satellites to download the data from. We choose 6 bands or wavelength channels that should, according to the literature, give us the best chance at predicting and detecting Pyro-CB. You can see these on the right now. As Emiliano explained earlier, we need to sieve through a lot of data, so we spend a lot of time creating an efficient parallelization pipeline using Apache Beam and data flow software packages. Thirdly, we use a pre-existing Pyro-CB detection algorithm developed at the Naval Research Laboratory, or NRL, to label our images. Again, you can see the output on the right, which shows the formation of a Pyro-CB cloud. Finally, we match meteorological and fuel data from a climate reanalysis model called ERA5. And so here are some examples from the outputs for relative humidity at the top here for 650 and 850 hectopascals, the wind at 10 meters and 250 hectopascals, and then also the available convective potential energy, or CAPE, and the surface latent heat flux. Altogether, these components give us our Pyro-CB database. To the best of our knowledge, Pyrocast is actually the first comprehensive database of Pyro-CB events. It is made up of 148 Pyro-CB events that are linked to 111 wildfires between 2018 and 2022. This represents over 40,000 hourly observations of wildfires in 6 wavelength channels and also 19 meteorological and fuel variables. Excuse me. Yes, so most importantly, this database is science and machine learning ready. This means that for the first time we can study these events in a systematic way, but also make inferences about the characteristics and the causes of Pyro-CB. So now I'm going to talk to you about the Pyrocast forecasting model. We use a convolutional neural network to predict whether wildfires will generate Pyro-CBs 6 hours ahead. The network is relatively shallow as to not overfit on the limited number of events that we have. We combine 6 wavelength channels and our meteorological and fuel variables as inputs, with the flags generated by the Pyro-CB detection algorithm as targets. The model outputs a binary classification using cross-entropy as a loss function. So using 17,000 observations with an 80-20 train test split, our best model is able to predict Pyro-CBs with an accuracy of 93%. This could give emergency responders enough time to evacuate safely from dangerous wildfires. On the right, we have a receiver operator curve for our best model. It plots the true positive rate as a function of the false positive rate. The dashed line shows the performance of a random classifier, and the model performance is shown with the continuous line. This graph shows that even when the threshold for predicting Pyro-CBs is very low, i.e. a low false positive rate, the model can confidently predict which wildfires will generate these events. The orange marker shows the true positive rate and false positive rate for a quoted accuracy. So now I'm going to pass on to Daniel, who will tell you more about the discovery framework.
Okay, thank you, Kenza. Yes, so for our Pyrocast discovery framework, we are interested here to using our machine learning pipeline to understand which parameters meteorological that could impact or are most important for the prediction of Pyro-CB or that make Pyro-CBs to happen. And what we see on the screen is a random forest classifier analysis where we run the test on our 19 meteorological parameters, and we came out with these 6 as the most important parameters for affecting or influencing occurrence of Pyro-CBs. So we see that the boundary layer height here at the bottom and the CAPE, which is the convective available potential energy, are the most important parameters for occurrence of or predicting the occurrence of Pyro-CBs. And so we also pushed our machine learning pipeline further by rather than just predicting the occurrence of pyroCVs in 6 hours time, like Kenza explained, we are interested to also use the pipeline to study or investigate which connections between the parameters are more important for prediction of pyroCVs. And yeah, what the architecture we use is just a simple or a modification of our architecture, the one Kenza talked about. But here we rather split into pathways, as we can see. And in one of the pathways, we introduce environment variables. The reason is that we expect that non-causal variables will need to be mixed with these environment variables to become predictive. And on the other pathway, we use the causal, we expect the causal variables which are not mixed with environment variables because they will be robust to predicting pyroCVs. So, and on the next slide, on this slide, we are looking at the results from that machine learning activity. So we see basically these five parameters is important, and then the links between them are more important. So for example, we are seeing that there is an important link between the relative humidity at 3,500 meters and the Cape, and also a link between the Cape and the haze, and so on. So we find these links are the important ones, but most important link of all ones is this one we indicated in the bold line, which is the link between the Cape and the 0.86 micron. These microns are the different channels or wavelengths of our geostationary images. And yeah, why or as an explanation or what could be responsible for this strong link is the expectation that the Cape, which is a measure of instability in the atmosphere around the fire, is important because it tells how much, how easy the smoke or plumes could be moved into the atmosphere upwards. And also the 0.86 micron actually presents information about the vegetation, which acts as fuel for the wildfire and pyroCV activity. So we found the two most important. And then, yes, so in summary of our contributions, we have developed the first comprehensive pyroCV database, which will enhance further studies of pyroCVs. And we have also developed the first pyroCV forecasting system in 6 hour ahead time. And additionally, we have used our machine learning pipeline to provide better understanding scientifically of the properties and causes of pyroCVs. So here we present to you the Pyrocast. We are super excited to present this to the society, and we expect that this will be a good channel to save lives and evacuate live people and improve resource allocation, especially during the occurrence of pyroCV. So thank you for listening.
Thank you very much, Aerosols team. That was a fantastic presentation. So now we're going to have a panel who will comment on the results and give us their thoughts for the future. I am delighted to welcome Pierre-Philippe Mathieu, who's the head of the ESA Explore Office, Alison Lowndes, who is Senior Scientist of Global AI at NVIDIA, Martina Butter, who is a Natural Catastrophe Specialist at Swiss Re, Rochelle Snyder dos Santos, Earth Observation Scientist at ESA, Zahan Barmal, Senior Director of Strategy at Google, Frederick Katzert, who is a visiting research scholar at Google also and an expert on hydrology, and Michael Obensteiner, who is Director of the Environmental Change Institute at the University of Oxford. Welcome and thank you for joining us.
Thank you.
So I'd like to start off maybe with Pierre-Philippe. Why do you think the new results and capabilities are important, and how will they address our needs?
Okay, first of all, I want to congratulate the team. I have witnessed really an evolution in the quality here since the beginning, and it was a really impressive presentation, I must say. Extremely good material. a very good narrative and high level content. So the famous expectations, I think, have been met. And I understand there is a lot of work and sweat and long night behind this. So again, congratulations. What I also notice is that the two use cases are touching on two things which are increasingly important for us. First one is simulation and prediction. And we have seen how the machine learning can fuse different data in order to project this into the future with some level of accuracy. That sometimes beats a state-of-the-art model because they are much more robust and they keep learning. And the other one is more physics-based and understanding of processes with a relationship between variables, which becomes increasingly important for the uptake of this technology by the scientific community. They really want to understand the black box and understand, let's say, how things are related together by physical principle. So I really like the two approaches here. One is very applicative for society, and the other one is more sciencey. And I think these results can be used. And if you look, for example, at the flood, what really resonates to me is that in the previous edition of FDL, you've been looking at the monitoring of flood and in particular the impact after the flood. Here you predict things so that you can anticipate. And in our strategy to put this on board and to react extremely fast to disasters and possibly anticipate this, this is a natural next step also for me. Imagine the satellite that can predict probability of risk and then automatically steer to some regions of interest. So I'm really pleased, and again, congratulations.
Fantastic. Thank you very, very much. Martina, what are your thoughts?
Can you hear me now?
We can hear you now, yeah. Fantastic.
Okay, sorry. So thank you very much for the invitation and for the very insightful presentation. You can clearly see there's a lot of work behind them. Thanks. Maybe a brief introduction for who is not familiar with the insurance world, the natural catastrophe in insurance world. I work as flood specialist, and I was very happy to learn about the application in flood predictions, very interesting for us. And in my role, I basically contribute to building and improving the flood modeling framework and to build a view of flood risk. So basically, in a nutshell, with our modeling framework, we basically overlap an hazard module, so flood prediction, with an exposure module, meaning potential exposure which can be hit from a flood in an area. And the goal is basically estimating a potential loss due to a flood. And we want to explore a spectrum of possible flood events, from the from the smallest ones and more frequent ones to the really catastrophic ones. So looking at the current natural catastrophe modeling landscape, I see this machine learning approach very innovative because so far more traditional, maybe more physically based model have been used. So I really appreciate this because I think flood is a very challenging peril to be modeled because it's because of its very local nature, and it requires really a lot of data for the modeling. So I think exploring new modeling approaches is very valuable at the moment. And it's very interesting for us, the fact that it aims at a global coverage, because ideally we would like to have to be able to model flood hazard globally with like a very homogeneous standard, but this is not possible. And as it was highlighted during the presentation, unfortunately, floods happen all around the world and very frequently. So that's highly appreciated. Of course, we're interested in this forecasting mode, although we work on different time scales, but the approach is very interesting for us. And another interesting point is the application to the flood mitigation and prevention, because this has a very good feedback on the insurance industry, because more mitigation and prevention means also adaptation, and so lower risk, which can hit also the insurance business. So these are, from my point of view, are the main valuable points.
Fantastic. Thank you. Does anyone have any responses or replies to make to Martina? Okay. Frederick, what were your main thoughts coming from the perspective of a flood modeler?
Yeah, thanks. So maybe for a little bit of context, I'm working at Google at the flood forecasting team that Zahan mentioned in his introduction. And I'm also the author of the caravan dataset that has been used in the study. So I'm very pleased to see, actually, I think it's probably the first application of this dataset, which is very new. And I think it's very exciting to see people make use of new datasets, open datasets. So my day-to-day work is quite similar to what has done here. So I can first off congratulate the team. I know it's a lot of work what they have done in the last weeks. I know it's quite challenging, and but I think there's a huge opportunity currently in this area, as the gap between what we currently have available as operational flood forecasting models and what can be done with the research results from like the previous years is quite huge. And a lot of exciting research is currently happening, and the team here definitely touched on this. So my thoughts are that, yeah, the team did amazing work. I think what we really need and what is missing is that we are missing globally observations for the areas that are most affected by floods. We have a lot of observations to train our models in areas of the world that are already covered by local models specialized to, for example, North America or Europe. But areas that are most affected by floods, like third world countries, developing countries, usually are quite sparse with observation data. And it is true, what the team also presented here, that we have ways to train models and apply them to different gauges. Still, we have seen from our day-to-day work that definitely it still helps to have data, at least from the region or from close by. And I think as like the whole community working in the field of flood prediction, we should work together towards trying to get a more open data, more shareable data, to collectively like make flood predictions better in the future.
That's great. Yeah, I know that data is a big issue in fires also, and it was a major issue for the Aerosols team. Has anyone got any comments on the usability and future-looking possibilities for the PyroCB work also? Maybe Michael, would you have some thoughts there?
Yeah, well, for PyroCB, well, first of all, again, I need to join the chorus of the others on congratulating the team to accomplish so much in little time. This is, as I understood, it's a 6-hour forecasting system. And what's interesting about it is how can we integrate this in operational systems that I actually, you know, currently I'm sitting here in France. France is hit by wildfires at the moment, and how can the operational systems really benefit from this? And there I have 2 comments. One is more technically. I think my understanding of the analysis is that it actually took instantaneous variables for the CNN analysis, and it would be interesting to look into lagged variables and cumulative variables to probably increase the predictive skill. The predictive skill is already very good, but false positives is also relatively high, and to my taste, a little bit too high. So some additional work on the predictive skill would really be good. And then see and share this information with these operational guys who, run observation stations on detecting fires instantaneously and so forth, and work a little bit on the larger system and integration of early warning systems, and then operational deployment issues for getting airplanes from other regions. Now I'm just sticking to the European example again, where we have a system where other countries are helping other countries. And if you have 6 hours lead time, you can actually fly a plane from, from Austria to France to actually help. And in this case, for these very operational decisions, 6 hour lead time on a PyroCB is really valuable information. So my recommendation is let's hook up to the operational guys and see what the opportunities for actual implementation is. Over.
Great, thank you, Michael. Rochelle, what are your thoughts?
Well, that was a great presentation. Thanks first for inviting me to join this showcase, which I hear with great interest because I work a lot with public health applications, air pollution, and high temperatures. So this was very applied to my area of research. Just to those that don't know about me, just a brief as well. I work at ESA together with Pierre-Philippe Mathieu in the PhilLab and in the AI applications for the Destination Earth initiative. Those that never heard about that is the young brother of Copernicus program. So this idea is to build digital twins in a higher spatial temporal resolution. So exactly the topic that we are talking today, so which is great. So I can provide a lot of great feedbacks on that. So these activities today is very aligned with the Destiny goals in developing these models to benefit society and help us to increase the knowledge before an event, flooding event happens. So first of all, I just thank you all the teams for these important topics in a very short time, like 8 weeks of very hard work. So congratulations to all. And I can highlight these activities are not just important for science, as we saw for the technical abilities in using artificial intelligence, using Earth observation in a wide range, but also, as I mentioned, for societal impact, for importance this to public health. And as we know, flooding affect negatively as the wildfires to the population. And then this is important for us to create alert systems that allows us to make this less impactful for our population worldwide. So in terms of feedback, actually from the projects, I was very happy to see the diversity that the teams used data. So I saw Earth observation satellites, I saw modeled and simulated data, for example, the ERA5 that was mentioned, observations directly measured by other systems, and also the diversity of your machine learning applications. So as we know, it's a very complex tasks to be able to forecast flooding systems. So sometimes one machine learning algorithm we're not able to do from X to Y and solve all the problems. So I saw that the teams have used two-stage machine learning approaches. So have used one machine learning application for one step, and then once this is solved, use machine learning for another one. I think this is a great idea and then helps us to deal with complexity. And as you mentioned as well, uncertainty around that. So, and one topic that, one thing interesting as well is the use of some other, let's say, technologies to bring this information at the end. So you solve, let's say you start doing data collection, machine learning applications, but in the end, how to communicate the results of that. with people that are non-experts in machine learning. So your visuals, your simulations showing, for example, the flooding was great, because these actually we can communicate with people that are not expert. What is the result of all these AI modeling and using Earth observation for that? I think this was a great communication strategy for that as well. And it should be used perhaps in the next showcases as an addition to how to use other technologies to implement the visualization of the projects. And I think I will stop here. Thank you.
Great, thank you. I know Alison is online too, but she hasn't been spotlighted because her video is not working. Alison, what are your thoughts?
Well, first of all, well done to everybody. Obviously, we're still in not brilliant times for working together as teams, but we have the virtual technologies, so we're excellent. But both of these topics are so relevant. I mean, as Michael said, understanding the apocalyptic pyro-CB will help everybody. I mean, even now, the UK's fire service are crying out, saying that we're ill prepared for this tinderbox situation, you know, right across Europe, across at least southern and, you know, Middle Earth, as we call it in the UK. They can put fires out, of course they can, but without, you know, let's say significant increase in resources, you know, society as a whole just is not ready for this unprecedented scale of risk from tinderbox situations, especially when the water you need, you know, this is the ironic thing, we're talking about floods in one place and fires in another where we have limited water to even put them out. You know, that's the state of the world. So we really have to get to grips with this. Deployment is always my focus. You know, that's what NVIDIA does, as well as the research, etc. And my personal view is that the tried and trusted models like LSTM can be put into orbit, but we really need to be using state-of-the-art here on the ground. You know, we need the kind of 100,000x speed up on the inference side that comes from using tech and you know, algorithms like for neural operators, for example. We have to bring all of this together. So I really, really want to see both teams' work implemented, you know, deployed to start helping in not only the prediction side, but the planning and the management. And, you know, we have to start deploying now. You know, we're literally on fire now, you know, or other people are, you know, while other people are flooding. So brilliant, brilliant work. You know, I am applauding. I know you can't see me. I can't figure out this camera. That's the state of the world. But yeah, wonderful. Thanks very much to everyone.
Thanks, Alison. And I think we all take your point about using the best models and the best algorithms that we can. But there's another point as well, to make sure that they're fed with the right data that doesn't have biases and is understood really well for confounding variables also. So we're almost out of time, but I'll just go over to Zahan for your thoughts also before we wrap up.
Thanks. I mean, again, I would just echo what my other panelists have said. Hugely inspiring work. Big congratulations to the teams involved. 3 reasons why I feel optimistic after this discussion. 1, I think this work shows again the power of AI tools when democratized to 10x science. Number 2, these presentations show the potential of technology to explore uncharted territories, to be implied in new environments, solving real critical problems. And 3rd reason, I feel optimistic. It's great to see this multidisciplinary work take place between domain experts and AI experts collaborating towards a common objective. So those are my final 3 thoughts, and congratulations again.